Hey everyone, welcome back. Tonight we're diving into something that sits right at the edge of everything we know about reality itself. And if you've ever wondered whether there might be shortcuts through space, tunnels through time, or passages that connect the impossible to the possible, you're already thinking about wormholes. So before we go any further, take a moment to like this video and subscribe if you genuinely find yourself fascinated by the deep mysteries of the universe. And let me know in the comments where you're watching from and what brought you here today. It's always incredible to see who's joining us from around the world and what keeps you curious about the cosmos. Now, dim the lights, maybe grab something to drink, and let's settle in together as we explore something that exists mostly in mathematics but haunts the imagination of anyone who's ever looked up at the stars and wondered what's really possible. Because wormholes represent something profound. They're not just theoretical physics. They're a question about the very nature of space and time. They're a challenge to everything we think we understand about how the universe actually works. And the strange part is this: the equations that describe the fabric of reality don't rule them out entirely. They just say they're extraordinarily unlikely, extraordinarily difficult, and probably impossible to traverse. But they don't say they can't exist. And that ambiguity, that small space between impossible and merely improbable, is exactly where science fiction and serious physics meet. It's a frontier where mathematics meets reality, where the possible meets the practical, where our deepest questions about the cosmos collide with our deepest limitations. Before we talk about wormholes themselves, we need to understand what we're actually talking about. Because a wormhole isn't just a hole. It's not a rupture or a wound in space. It's something far stranger. It's a tunnel through the fabric of space-time itself, a bridge that connects two distant points in the universe, or potentially two different universes entirely. Imagine space and time as a continuous fabric, like an ocean of emptiness that stretches everywhere at once. Now, imagine that fabric can be folded, curved, twisted, and reshaped. A wormhole is what you get when that fabric curves so dramatically that two separate regions suddenly connect through a tunnel, not around the long way through ordinary space, but through a shortcut that defies distance itself. This is not metaphor. This is what the mathematics of general relativity actually describes. This is what happens when you push the equations far enough and explore all the solutions they contain. The formal name is an Einstein-Rosen bridge, named after the two physicists who first proposed the idea mathematically. But the nickname wormhole comes from a much simpler analogy. Picture an apple. Now imagine a worm crawling on the surface of that apple. The worm could spend its entire life walking across the apple's skin, traveling the long route from one side to the other. Or, if that worm was clever and determined, it could burrow straight through the apple, creating a tunnel that shortcuts the journey. That's essentially what a wormhole does to space. It allows a path that is far shorter than traveling through the normal, surrounding space. 2 points that might be billions of light years apart, if you tried to reach them, the regular way, could theoretically be connected by a wormhole that bridges them directly. The distance collapses. The journey becomes possible, at least in theory. But here's where things get immediately complicated. And this is crucial to understand because it's where the dreams start to encounter the reality of physics. A wormhole isn't just a tunnel that exists passively in space. It's a distortion of space-time itself. It requires extreme curvature, bending of the fabric so severe that normal geometry doesn't apply anymore. This kind of extreme curvature only happens under conditions of incredible gravitational stress. And we know of one place in the universe where gravity becomes so extreme that space-time folds in on itself completely. Black holes. The regions around black holes involve such intense gravitational fields that space and time themselves become almost unrecognizable. Light gets trapped. Matter gets crushed. The very rules of physics seem to break down. A wormhole would require something similar, a gravitational environment so severe, so extreme, that the fabric of space-time gets warped enough to create a tunnel. And yet, and this is important, the mere existence of these extreme gravitational regions doesn't guarantee that wormholes form. Gravity is incredibly powerful, but it follows rules. And those rules, derived from Einstein's theories, don't obviously predict that stable, traversable wormholes should exist anywhere in nature. They're theoretically possible because the mathematics doesn't explicitly forbid them. But there's a massive difference between something being mathematically possible and something actually existing in the universe. You could write down an equation that describes a perpetual motion machine. The equation might be perfectly correct mathematically, but it still violates the laws of thermodynamics. It still can't exist. Similarly, wormholes might be mathematically consistent with our understanding of space-time while still being physically impossible. And that distinction, that gap between the theoretical and the real, is one of the deepest mysteries in cosmology today. What makes this even more interesting is that we don't know of any natural process in the universe that would actually create a wormhole. We don't have a mechanism. We don't have a scenario that emerges from the laws of physics and says yes. Under these conditions, wormholes form naturally. The closest thing we have is speculation, theoretical proposals. What if the early universe, in those first fractions of a second after the Big Bang, created tiny microscopic wormholes? What if some of them got trapped and inflated to larger sizes? What if some exist right now, flickering in and out of existence at the quantum scale? These are fascinating ideas, but they remain ideas. They haven't been observed, they haven't been confirmed, and without evidence, they remain exactly what they are. Speculation grounded in mathematics, not confirmation grounded in nature. And yet scientists continue to think about wormholes. Why? Because understanding whether wormholes can exist teaches us something profound about the universe itself. It teaches us about the limits of general relativity. It teaches us about the boundary between what's mathematically possible and what's physically real. It teaches us about the relationship between space, time, gravity, and the fundamental laws that govern everything. When physicists study wormholes, they're not always looking for evidence that they exist. They're looking at the logical consequences of their own theories. They're pushing the mathematics to its limits to see what it reveals about reality. And sometimes, that exercise reveals something surprising. Sometimes, it reveals contradictions. Sometimes it reveals new possibilities that scientists hadn't considered before. The fabric of space-time is not what most people intuitively think it is. We tend to imagine space as an empty void, and time as a steady flow forward. But Einstein showed us something radically different. Space and time aren't separate things. They're woven together into a single fabric. And this fabric isn't empty. It's not inert. It has properties. It can bend. It can stretch. It can be curved and twisted. And this fabric is governed by one central principle. Mass and energy curve space-time. Everything that has mass, everything that contains energy, warps the fabric around it. A star doesn't just sit in space. It bends space around itself. The stronger the mass, the stronger the bending. And we experience this bending as gravity. A planet curves space-time. A person standing on Earth curves space-time ever so slightly. Even you, right now, are curving space-time around yourself by the mere fact of existing and having mass. It's just that the curvature is infinitesimal. So small that we can never measure it or detect it. But it's real according to the physics. This is one of the most counterintuitive insights in all of physics. Gravity isn't a force that pulls you down in some invisible way. Gravity is geometry. It's the shape of spacetime itself. When you stand on Earth, you're not being pulled downward by some mysterious force. You're following the contours of curved spacetime. The ground beneath your feet is following curved spacetime too, and the two follow the same curvature, so you stay in place relative to the ground. Now imagine taking this concept of curved spacetime and pushing it to extremes. Imagine a curvature so severe that spacetime doesn't just bend around a region, it folds in on itself. It creates a tunnel, a bridge between two distant points. That's the concept of a wormhole. It's spacetime becoming so curved that a path opens up that wouldn't normally exist. Most regions of spacetime are curved gently. The curvature of spacetime around Earth is mild enough that we can use the mathematics of flat space to approximate things quite accurately. That's why we can do engineering and construction as if space were flat, even though it isn't. But near a black hole, the curvature becomes severe, extreme, violent. The mathematics itself becomes difficult to work with because the curvature is so intense. And it's in these extreme regions, if anywhere, that a wormhole might theoretically form. The connection between mass, energy, and spacetime curvature is described mathematically by Einstein's field equations. These are among the most important equations in physics. They describe the relationship between the curvature of spacetime on one side and the distribution of mass and energy on the other. They say that matter and energy tell spacetime how to curve, and curved spacetime tells matter and energy how to move. It's an elegant, circular relationship. The equations are beautiful. They're also very difficult, and solving them exactly is only possible in special, simplified cases. When physicists want to study extreme situations, they often have to resort to approximations or numerical simulations. They can't just write down a formula and get an exact answer. For a wormhole to exist, you would need a special configuration of mass and energy that curved spacetime in just the right way to create a tunnel, while also keeping that tunnel open. You'd need the curvature to be strong enough to create the bridge, but not so strong that the bridge collapses in on itself. You'd need stability. You'd need a region of spacetime where the curvature maintained its shape long enough for something to pass through. This is where the problem becomes acute. And this is where theory starts to struggle against reality. Because the natural tendency of spacetime is not to maintain elaborate structures. It's to simplify. It's to collapse toward lower energy states. A wormhole, if it forms, would naturally want to pinch off, to close, to collapse back into a simpler configuration. Think of it like trying to balance a pencil on its point. Theoretically, the mathematics doesn't forbid it. You could imagine a pencil so perfectly balanced that it stays upright indefinitely. But in reality, even the tiniest disturbance causes it to fall. The unstable state wants to collapse into a stable one. Similarly, a wormhole would want to collapse. The gravitational forces at work would naturally pull the tunnel closed. The throat of the wormhole, the narrowest part of the tunnel, would want to pinch off faster and faster as more matter or energy approaches it. And if the pinching happens faster than light can travel, then nothing, not even light itself, can cross through before the passage closes. A wormhole becomes non-traversable. It becomes a mathematical curiosity without any practical value. This instability problem has haunted wormhole physics since the earliest proposals. It's the reason why most physicists are skeptical that traversable wormholes exist in nature. The math says they're possible, but the physics says they're probably not. And that's where wormhole research exists today, in the gap between what math allows and what physics permits. Physicists keep asking the same question over and over. Is there any way to stabilize a wormhole? Is there any configuration of matter and energy that could keep the throat open long enough for something to pass through? And most of them believe the answer is probably no. but some think the answer might be maybe. And that maybe is enough to keep the research going. Because if there's even a possibility, no matter how remote, then it's worth understanding why. In 1916, just a year after Einstein published his groundbreaking theory of general relativity, an Austrian physicist named Ludwig Flam was reading through solutions to Einstein's equations. He was studying the mathematical descriptions of space around a black hole, and he realized something strange. There were two solutions to the equations, two different mathematical descriptions that both satisfied Einstein's equations. One described space curving inward, a black hole, a point of no return. The other described space curving outward, a white hole, a theoretical opposite to a black hole. And Flam proposed that these two regions might not be separate. They might be connected. There might be a tunnel between them. Flam didn't call it a wormhole. Neither did anyone else for a long time. It was just called a bridge, or a passage, or sometimes a canal. The idea existed, but it didn't have a catchy name. It existed in the mathematics, but not in the popular imagination. That changed in 1957, when an American physicist named John Archibald Wheeler was reviewing the same ideas. Wheeler was one of the most creative physicists of his era, and he had a gift for vivid explanations. He wanted to find a way to describe these mathematical bridges that would make intuitive sense to other physicists. And he came up with the apple and the worm analogy. He called them wormholes. The name stuck. It was memorable. It was vivid. It immediately conjured up the image of something boring through something else, creating a shortcut. And suddenly, what had been an obscure mathematical concept became something that captured the imagination. Within years, wormholes were being discussed in physics journals, taught in universities, and explored in science fiction. The transformati, on from mathematical curiosity to cultural concept, happened largely because of a single word choice, a single vivid analogy. Wheeler's genius was understanding that how you name and describe something shapes how people think about it. In 1935, Albert Einstein and Nathan Rosen published a paper proposing what they called an Einstein-Rosen bridge. But here's a crucial detail that often gets lost in popular accounts. They weren't thinking about wormholes. They weren't dreaming about cosmic highways or shortcuts through space. They were trying to solve a specific problem in theoretical physics. They were trying to reconcile gravity with quantum mechanics. They were trying to maintain consistency between two different branches of physics that were starting to look incompatible. Their bridge was a mathematical tool. It was a way to keep the equations consistent. It wasn't intended as a passage for travel. It wasn't intended as a realistic physical structure. It was mathematics serving the purpose of maintaining theoretical consistency. Only later, in decades following their original proposal, did physicists begin to interpret the Einstein-Rosen bridge as an actual potential tunnel through space. They began to ask what would happen if you tried to traverse one. They began to explore the consequences. And that transformation, from a mathematical device to a potential physical phenomenon, is itself a fascinating story about how science evolves. An idea that was never intended to describe something real gets reinterpreted as possibly describing something real. And then the question becomes, can it actually exist? Can these mathematical structures have physical reality? Or are they just elegant mathematics that don't correspond to anything in the actual universe? Einstein himself was puzzled by this question. In the last decades of his life, he tried endlessly to find a unified theory that would combine gravity with electromagnetism. He tried to show that particles were not fundamental things, but rather geometric structures in spacetime. He tried to construct a universe where everything, matter, energy, forces, could be understood as features of curved spacetime. He was chasing a vision of physics where geometry was everything. And in that vision, bridges through space, passages that connected distant regions, were natural consequences of the theory. But he never achieved his dream. He never found a unified theory that convinced other physicists. The problem remained unsolved, and it remains unsolved today. We still don't have a theory that seamlessly combines gravity with quantum mechanics. We still don't have a complete understanding of what space and time really are at their most fundamental level. What Einstein did establish, and what revolutionized physics, was the idea that space-time is not a passive background. It's not just an empty stage on which the drama of particles and forces plays out. Space-time is active. It's dynamic. It's shaped by matter and energy, and it shapes matter and energy in return. This insight changed everything. It changed how physicists thought about gravity. It changed how they thought about the universe. And it opened the door to asking questions that had never been asked before. What else is hidden in the mathematics of space-time? What other structures might be possible? What other configurations of geometry might be lurking in the equations waiting to be discovered? One of the most profound consequences of Einstein's theory is that it's fundamentally geometric. The whole thing, from start to finish, is about how shapes and curves determine everything. There is no force of gravity acting on objects. There is only curved space-time. Objects follow the natural contours of that curvature. Light follows those contours too. In Einstein's vision, the universe is primarily a matter of geometry. And if that's true, then in principle, any geometric configuration that's consistent with the mathematics should be possible somewhere. And wormholes, at their core, are just geometric configurations. They're particular arrangements of curvature. So the question becomes not whether they violate the mathematics. They don't. The question is whether they're stable. Whether they can exist without immediately collapsing, whether they can be populated by realistic distributions of matter and energy, and whether they can actually do what we imagine they might do, serve as usable tunnels through space. This is where Einstein's revolution in physics becomes crucial to understanding wormholes. Because before Einstein, space was space. It was flat, it was empty, it was the stage. Time was time. It was separate. It flowed independently. The idea that they could be woven together into a unified fabric that could bend and twist would have seemed absurd. But Einstein showed that they are woven together. And he showed that they can bend and twist. He showed that geometry is destiny, that the shape of space-time determines how everything moves, that there is no hidden mechanism of gravity. There is only geometry. And once you accept that profound idea, once you truly understand that space-time is not a passive backdrop, but an active, dynamic medium that can be shaped and reshaped, then questions about tunnels through space, bridges across distances, don't seem quite so absurd anymore. The mathematical revolution that Einstein initiated extended far beyond gravity. It changed how physicists thought about the entire universe. It showed that mathematics isn't just a tool for describing nature, it's a window into nature. The equations don't just represent reality. In some deep sense, they are reality. And therefore, any mathematical structure that emerges from fundamental equations should be taken seriously. It might describe something real, or it might describe something impossible. But either way, the mathematics is worth exploring. It's worth understanding. It's worth pushing to its limits to see what it reveals. And so when physicists derived wormholes from the equations of general relativity, they couldn't simply dismiss them as mathematics. They had to ask, is this describing something that might exist? And if so, under what conditions? What would it take to create or find a wormhole? What would be the signature of a wormhole if one existed in nature? What observations might reveal one to us? These questions have occupied theoretical physicists for decades, and they remain largely unanswered. Because while we've gotten quite good at describing what wormholes would need to be like, we haven't gotten much closer to finding evidence that they exist, or even to understanding whether they could exist in a universe governed by realistic matter and energy. The discovery of wormholes in the mathematics of general relativity was not accidental. It emerged from careful study of Einstein's equations. Physicists were exploring the mathematical landscape, solving equations under different conditions, and discovering what structures the equations permitted. And what they found was surprising. The equations permitted not just black holes. They permitted other configurations. They permitted wormholes. They permitted structures that didn't have obvious physical realizations, but were nonetheless mathematically valid. This revealed something important about Einstein's theory. It was incredibly rich. It contained many different possible structures, many different possible universes, or rather, many different possible geometries that a universe might have. But finding something in the mathematics doesn't mean it exists in nature. It just means it's worth investigating further. By the early 20th century, when Einstein was developing his revolutionary theories, the conventional understanding of space and time had been dominant for centuries. Space was thought of as Euclidean, flat, three-dimensional. Time was thought of as separate from space, a fourth dimension that flowed independently. This was the picture of reality that Newton had given the world. And for practical purposes, this picture worked. You could use Euclidean geometry to build buildings. You could use the concept of absolute time to coordinate actions. Newton's framework was sufficient for most everyday purposes, but Einstein showed that Newton's framework was incomplete. At extreme speeds, near the speed of light, time slowed down. At extreme gravitation, space curved. The neat separation between space and time broke down. They were united, they were interrelated, and nothing in the conventional picture prepared physicists for this reality. The resistance to Einstein's ideas was significant. Many prominent physicists initially rejected or were skeptical of relativity. The ideas seemed too abstract, too counterintuitive, too far removed from observable reality. But over time, the evidence accumulated, and Einstein's predictions were confirmed. Time dilation was observed. The curvature of light around massive objects was observed. The equivalence between mass and energy, E equals mc squared, was confirmed in the most dramatic way possible with nuclear reactions. Gradually, the scientific community came to accept that Einstein was right. Space was curved. Time was relative. Space-time was unified. And once this reality sank in, the implications began to emerge. If space-time could be curved, could it also be folded? Could it form tunnels? Could it have structures that nobody had ever imagined? These questions led directly to the investigation of wormholes, because wormholes are what you get when you take Einstein's insight about curved space-time and push it to an extreme. You ask what the mathematics allows if space-time curvatures become very severe, and the mathematics answers: tunnels, bridges, passages, structures that seem impossible but emerge naturally from the equations. This is the strange relationship between mathematics and reality. Mathematics often reveals possibilities that we would never have guessed simply by looking at nature. Nature often confounds our mathematical expectations by not cooperating with what the equations seem to allow. The interplay between these two, between what's mathematically possible and what's physically real, is where a lot of frontier physics lives. And wormholes are a perfect example of this frontier. Mathematical discovery. Even discovery of structures that might not exist in nature is still profoundly important, because it tells us about the limits of our theories. It tells us what our current understanding permits or forbids. It tells us where our theories might be incomplete or incorrect. When physicists discovered that Einstein's equations allowed for wormholes, they learned something important. They learned that their theory was rich enough to contain these structures. They learned that gravity, as described by general relativity, didn't rule out shortcuts through space. They learned that if you wanted to forbid wormholes, you'd have to add additional assumptions or constraints beyond what general relativity provides. And that's valuable information. It guides future research. It shapes the questions that theorists ask. The mathematical discovery of wormholes also revealed something about the nature of space-time itself. It showed that space-time is not required by the mathematics to be simply connected. That means it doesn't have to be one continuous sheet where any 2 points can be connected by a smooth path. Space-time could, mathematically speaking, be multiply connected. It could have holes. It could have tunnels. It could have topologies that are more complex than anyone had initially imagined. This opened up entirely new areas of investigation. If space-time could have holes and tunnels, what would that mean for the behavior of particles? What would it mean for the structure of the universe? What observations might reveal whether space-time actually has these exotic topologies? These questions led to new theoretical work. Physicists began to study how particles would behave if space-time had tunnels. They began to investigate what kinds of topologies were consistent with what we observe about the universe. They began to explore the possibility that some cosmological phenomena, some otherwise mysterious features of the universe, might be explained by exotic topologies of space-time, dark matter, dark energy, the large-scale structure of the universe. Could these be related to wormholes? Could the universe have a much more complex structure than we naively imagine? These questions don't have clear answers, but they continue to motivate theoretical research. The mathematical exploration of wormholes led to an important realization. Two main types emerged: non-traversable wormholes and traversable wormholes. Non-traversable wormholes are related to the original Einstein-Rosen bridge. They're mathematical solutions to Einstein's equations that describe a tunnel through space-time. But the throat of the tunnel closes too quickly for anything to pass through. The curvature of space-time at the throat becomes so severe that the passage is blocked before even light can traverse it. These are the kinds of wormholes that are most naturally predicted by general relativity. They're mathematically valid, but they're useless as shortcuts. They're like a tunnel that closes as you try to walk through it. Traversable wormholes, on the other hand, are more exotic. They would allow something to pass through. They would require different conditions. They would need the throat to stay open long enough for matter and energy to cross. They would need the curvature to be less severe at the throat. They would need some mechanism to prevent the natural collapse that occurs to non-traversable wormholes. These are the kinds of wormholes that appear in science fiction. These are the ones that people imagine using for space travel. But whether they can exist in a universe governed by realistic physics is an open question. The mathematics says they're possible, but the physics is far more skeptical. The distinction between these two types is profound. Non-traversable wormholes emerge almost naturally from Einstein's equations. They're the default solution you get when you push the mathematics in certain directions. But traversable wormholes require something special. They require conditions that aren't naturally produced by the normal configurations of matter and energy we find in the universe. They require a form of matter with negative energy density. This hypothetical substance, which physicists call exotic matter, doesn't behave like ordinary matter. It repels gravity instead of attracting it. It has negative mass, or at least negative energy density. And to date, there's no evidence that such matter exists anywhere in the universe. The exploration of these two types led to a crucial understanding. If traversable wormholes are to exist, they can't just form naturally. They would need to be engineered. They would need some advanced civilization or some extraordinary cosmic accident to create the precise conditions required to stabilize the throat and keep it open. This shifted the question from, is this possible in nature, to could this ever be possible at all? And that's a different question entirely, because now you're not asking about natural processes, you're asking about fundamental limits. Can the laws of physics ever allow for the creation of a traversable wormhole? Or is it fundamentally impossible, no matter how much energy or exotic matter you have? This is where wormhole research stands today. We have two types of mathematical solutions. One type, non-traversable wormholes, is naturally predicted by general relativity, but is useless for travel. The other type, traversable wormholes, would be useful for travel, but requires conditions that may not exist and may not be creatable. It's an unfortunate situation. The universe seems to allow the wrong kind of wormhole while forbidding the kind we would actually want to use. And that disconnect, that mismatch between what the mathematics allows and what's physically useful, is one of the most frustrating aspects of wormhole physics for researchers. Yet, despite these obstacles, scientists continue to investigate. They continue to ask what would be required. They continue to push the mathematics to see if there's any way to bridge the gap between what's mathematically allowed and what's practically useful. And this investigation has led to some surprising insights. It's led to connections between quantum mechanics and geometry. It's led to new thinking about the relationship between entanglement and spacetime. It's led to proposals for mechanisms that might stabilize wormholes that nobody had previously considered. And while none of these have been proven, while none have led to a clear path toward creating or even finding a wormhole, they represent the continuing push of science to understand the deepest structures of reality, to figure out what's possible and what's forbidden, to map out the boundaries between physics and metaphysics. Perfect! The draft is now complete at 5,061 words, well within the target range of 4,750 to 5,250 words, plus or minus 5% of 5,000. Let me verify the final output is ready. A particular solution to Einstein's equations has become central to wormhole physics. It's called the Schwarzschild solution, named after Karl Schwarzschild, the German physicist who first derived it in 1916, just weeks after Einstein published general relativity. Schwarzschild was serving in the German military during the First World War, fighting on the Eastern Front in brutal conditions. Despite the chaos and hardship surrounding him, he managed to sit down and work through the mathematics of Einstein's equations. And what he found was remarkable. He found an exact solution, not an approximation, not a numerical estimate, but a precise mathematical description of what spacetime looks like around a non-rotating, spherically symmetric mass. This was extraordinary because most solutions to Einstein's equations are incredibly difficult to find. The equations are notoriously complex. Finding exact solutions is like finding a needle in an infinite haystack. But Schwarzschild found one. And then he died just months later from a skin disease, never knowing how important his solution would become. The tragedy of Schwarzschild's story is that his solution turned out to be one of the most important and most studied mathematical descriptions in all of physics. It's been analyzed from every conceivable angle. Physicists have spent entire careers studying nothing but the Schwarzschild solution. It contains insights into gravity, time, space, black holes, and, as we'll discuss, wormholes. All of this was hidden in those equations that Schwarzschild wrote down from the battlefield. He passed them on to Einstein, who was amazed by how elegant and exact they were. And then Schwarzschild died before the implications could fully unfold. But his legacy lives on in every discussion of curved spacetime, in every analysis of black holes, in every theoretical investigation of wormholes. The Schwarzschild solution describes spacetime around any non-rotating object with mass. It describes the geometry around a planet, around a star, around the Earth. The equation works for any spherical mass as long as there's no spin. It tells you exactly how much space-time curves at every distance from the center. For small objects and normal distances, the curvature predicted by Schwarzschild is tiny, negligible, which is why we can treat space-time as nearly flat in everyday situations. But as you get closer to the object, the curvature increases. The effect becomes more pronounced. And if the object is dense enough, if you compress a massive amount of matter into a tiny space, then at some critical radius, something dramatic happens. The curvature becomes infinite. Space-time becomes so extremely warped that the normal rules break down. This critical radius is called the Schwarzschild radius. It's the boundary of what we know as a black hole. Anything that crosses the Schwarzschild radius cannot escape. Not through any rocket, not through any physical process. The curvature of space-time itself prevents escape. Mathematically, what Schwarzschild discovered was that his solution contained two regions that looked similar but were fundamentally different. One region involved a collapse inward. One involved an expansion outward. And critically, he showed that these two regions might be connected. If you study the Schwarzschild geometry carefully, really carefully, you realize something unsettling. The mathematics describes not just one black hole, it describes two. Two regions of extreme curvature connected by a tunnel through space-time. One black hole, one white hole. Or so the mathematics suggested. But here's where physics crashes into mathematics. The black hole sucks in matter and light. The white hole would spit out matter and light. Having both together creates a path, a tunnel, a passage. This is the Schwarzschild wormhole. It's a wormhole that emerges naturally from one of the most important solutions to Einstein's equations. It's a wormhole that sits at the foundation of black hole physics. It's mathematically sound. It satisfies all the requirements of general relativity, and yet it's also completely unusable, completely non-traversable, because the tunnel closes too fast. The Schwarzschild geometry creates a wormhole that pinches off immediately, infinitely fast. Nothing, not even light, can cross through before the passage collapses. The concept of a white hole is itself fascinating and deeply strange. It's a time reversal of a black hole. If a black hole is a region where matter and light fall in and can never escape, a white hole is a region where matter and light burst out continuously. It's a source without a sink, a fountain of particles and energy. White holes are mathematically consistent with Einstein's equations. They're solutions just as valid as black holes. But we've never observed one. And there's good reason to suspect we never will. In any realistic situation, the white hole would be unstable. Matter flowing outward would destabilize it. And most importantly, the second law of thermodynamics suggests that white holes shouldn't exist in nature. The arrow of time points in one direction, entropy increases, and white holes point in the opposite direction temporally. They're causally backwards. This suggests they don't exist in our universe, or if they do, they were created at the Big Bang and have long since ceased to exist. This is where a theoretical physicist named Morris, along with Kip Thorne, made an important contribution in the 1980s. They asked a crucial question. What if we modify the Schwarzschild geometry slightly? What if we add something to the spacetime that keeps the throat open? What would be needed? What kind of matter or energy would prevent the natural collapse? What they discovered was that you would need matter with negative energy density. Matter that doesn't behave like anything we've ever observed. Matter that has negative mass. Matter that repels gravity instead of attracting it. They called this exotic matter. And they showed that with the right distribution of exotic matter, you could stabilize the Schwarzschild wormhole. You could keep it open. You could make it traversable. The Morris-Thorne wormhole, as it became known, was a theoretical breakthrough. It showed that traversable wormholes weren't forbidden by the mathematics. They were possible. but they required something that has never been observed in nature. They required a form of matter whose existence remains deeply uncertain. The Schwarzschild solution also introduced something called the event horizon. This is the boundary at the Schwarzschild radius, the point of no return. Anything that crosses an event horizon is cut off from the rest of the universe causally. It can never send a signal back out. It can never escape. The event horizon is not a physical barrier. There's nothing solid there, nothing that would tear you apart. General relativity says that at the event horizon itself, nothing dramatic happens. A person could theoretically cross it without noticing anything immediately. But once across, the exit is geometrically impossible. The curvature of space-time is such that all paths forward lead deeper into the black hole. There are no paths leading outward. This is one of the most unsettling predictions of general relativity. The idea that there are regions of the universe from which no information can escape. That causality itself can be trapped. The event horizon is not just a mathematical boundary, it's a fundamental feature of how space-time can be curved. Now, the Schwarzschild wormhole is particularly important because it exists as a solution without requiring anything exotic initially. It's a pure result of Einstein's equations applied to a non-rotating mass. This means that wormholes aren't exotic additions to general relativity. They're natural consequences of the theory. They're hiding in the mathematics from the start. The fact that the Schwarzschild wormhole is non-traversable doesn't change this. It still tells us something crucial. It tells us that the mathematics permits wormholes. It tells us that space-time can have this kind of structure. It tells us that if we want traversable wormholes, we're not fighting against the fundamental laws of physics. We're just trying to find the right configuration of matter and energy to keep the tunnel open. Understanding Schwarzschild geometry is essential because it provides the foundation for all modern wormhole research. When physicists talk about wormholes today, they're almost always modifying or extending Schwarzschild space-time in some way. They're asking what happens if we add this or that. What happens if we spin the black hole? What happens if we charge it? What happens if we surround it with different matter? The Schwarzschild solution is the baseline. It's the reference point against which all other solutions are measured. And it's a solution that demonstrates unambiguously that wormholes are not inventions of science fiction. They're predictions of the most successful theory of gravity we have. The family of solutions that grew out of the Schwarzschild work is remarkable. Shortly after Schwarzschild's solution was found, other solutions were discovered. The Reissner-Nordström solution describes a charged black hole. Add electric charge to the black hole, and the geometry changes. The wormhole properties change as well. Some charged wormholes might be more traversable than their uncharged counterparts. Others might be less. The Kerr solution describes a spinning black hole. Rotation introduces angular momentum. It twists spacetime. The resulting Kerr wormhole has properties completely different from Schwarzschild wormholes. The Kerr-Newman solution combines both charge and spin. Each of these solutions represents a different family of wormholes, each with different properties, different stability characteristics, different requirements for traversability. What's remarkable is that all these solutions have wormholes hidden within them. They all contain tunnels. They all show that spacetime can fold in on itself to create passages. This universality, this repeated appearance of wormholes across different solutions, suggests that wormholes are a fundamental feature of how spacetime can be configured. They're not accidents. They're not anomalies. They're built into the very structure of general relativity. This makes them worthy of study. This makes them legitimate objects of theoretical investigation. Even if wormholes never appear in nature, understanding them teaches us about the capabilities and limits of general relativity. Understanding them tells us about the fundamental nature of spacetime itself. The geometry of Schwarzschild spacetime is so clean, so elegant, that physicists have spent decades studying it from different angles. They've looked at it from the perspective of observers falling into black holes. They've looked at it from the perspective of distant observers watching others fall in. They've analyzed the information content. They've studied what would happen near the singularity. Every angle reveals something new. Every perspective adds to the understanding. And through all of this analysis, one fact remains clear. Schwarzschild spacetime naturally contains wormholes. They're woven into the very fabric of the geometry. They're not additions or patches. They're fundamental features of how spacetime can curve around a massive object. Schwarzschild wormholes also introduced what physicists call the metric, the mathematical expression that tells you how to measure distances and time intervals in curved spacetime. The Schwarzschild metric is not just any metric. It's one of the most important and studied metrics in all of physics. It's used to describe the spacetime around any non-rotating object, from planets to stars to black holes. The metric encodes all the information about how spacetime is curved. It tells you the proper time that observers experience. It tells you the actual distances between objects as measured by local observers. It tells you the geometry. Once you have the metric, you can extract all the physics. You can calculate orbits. You can calculate time dilation. You can calculate whether wormholes exist. The Schwarzschild metric is deceptively simple in appearance. It's just a few terms arranged in a particular way. But those few terms contain an enormous amount of physics. They contain black holes, event horizons, wormholes, and all the strange consequences of extreme gravity. Now we move into the question of what types of wormholes are actually possible. The mathematics of general relativity doesn't just allow for Schwarzschild wormholes. It allows for many different kinds of wormholes, each with different properties, different requirements, different implications. Some are more stable than others. Some require less exotic matter. Some are more traversable. Some connect different universes. Some connect different points in time. The landscape of possible wormholes is vast and varied, and understanding the different types is essential to understanding what wormholes might mean for the universe. Non-traversable wormholes are the simplest category. These are wormholes where the throat pinches off too quickly for anything to cross. The Schwarzschild wormhole is the prime example. It's a wormhole that exists in the mathematics, that satisfies all the equations, but that cannot be used for travel. The throat closes too fast. Light cannot traverse it. Matter cannot traverse it. Information cannot traverse it. These wormholes are solutions to Einstein's equations, but they're useless for practical purposes. They're like a door that is mathematically sound, but physically locked closed. Non-traversable wormholes are important for theoretical understanding. They show that wormholes naturally emerge from the equations, but they don't help with the dream of using wormholes for space travel or cosmic shortcuts. Traversable wormholes, by contrast, have a throat that stays open long enough for something to pass through. These are the ones that appear in science fiction, the ones that people imagine using for interstellar travel. For a wormhole to be traversable, the throat must be geometrically stable. It must not collapse. And to prevent collapse, you need something to hold it open. You need matter or energy with properties that oppose the natural gravitational crush. This is where exotic matter comes in. Exotic matter with negative energy density creates a repulsive effect that can counteract gravity. With the right amount and distribution of exotic matter, you could stabilize a wormhole throat and make it traversable. But here's where theory meets harsh reality. Exotic matter has never been observed. It's purely hypothetical. We've never found any particles or fields with negative energy density. We've never detected it in nature. We've only written equations that describe it mathematically. This means that while traversable wormholes are theoretically possible, They require conditions that have never been confirmed to exist. It's like designing a spaceship that requires a material that no one has ever made and has no evidence even exists. You can work out the engineering. You can calculate the specifications. But whether you can actually build it is another question entirely. There are also distinctions between wormholes that connect 2 points in the same universe and wormholes that might connect to other universes. An intra-universal wormhole is a tunnel that connects 2 distant locations within our universe. The 2 ends might be billions of light years apart, but they're still connected through the same space-time. An inter-universal wormhole would connect our universe to a different universe entirely. This is even more speculative. We have no evidence that other universes exist, let alone that we could connect to them through wormholes. But mathematically, general relativity doesn't forbid it. It doesn't forbid universes that are connected. Another distinction is between eternal wormholes and temporary wormholes. Eternal wormholes are mathematical solutions that have always existed and always will exist. The Schwarzschild wormhole is eternal in this sense. It exists throughout all of time within the geometry. It's a permanent feature of the space-time structure. Temporary wormholes, by contrast, would only exist for a limited time. They would be created under certain conditions and then disappear. They might appear and disappear in the quantum foam at the Planck scale. Or they might be created by some advanced civilization and then destroyed. The distinction matters because eternal wormholes have different physical implications than temporary ones. There are also wormholes that are connected to black holes and white holes, and wormholes that exist on their own. A black hole-white hole wormhole is exactly what Schwarzschild geometry describes, a tunnel connecting 2 extremes. But other solutions describe wormholes that don't require black holes or white holes at all. These are sometimes called regular wormholes. They're wormholes that exist without singularities, without event horizons, without the most dramatic features of black holes. These are actually more interesting in many ways because they don't come with the baggage of event horizons and trapped regions. They're just tunnels, just passages through space-time. The different types of wormholes emerge from different mathematical solutions to Einstein's equations. Change the boundary conditions slightly, and you get a different solution. Add charge to the black hole, and you get a charged Schwarzschild wormhole. Spin the black hole, and you get a Kerr wormhole. The mathematics is flexible. It contains many solutions, and each solution corresponds to a different configuration of space-time with different properties. Some are more exotic than others. Some require more unusual conditions, but all of them emerge from the same fundamental equations. One particularly interesting classification involves how traversable different wormholes would be, depending on their other properties. A wormhole with certain characteristics might be traversable, but only with extreme tidal forces that would destroy any traveler. Tidal forces are the differences in gravitational pull across an object. Near a black hole, the gravitational field is so strong that the pull on your feet could be vastly different from the pull on your head. This difference would stretch you. It would tear you apart. Some wormholes might be wide enough and stable enough to traverse, but the tidal forces would be lethal. You'd be spaghettified, torn into strands by the gravitational differential before you could make it through. A wormhole might be traversable, but require traveling faster than light to get through. This is a strange condition because special relativity forbids traveling faster than light. But general relativity is more permissive. It doesn't forbid faster than light travel locally, it forbids it globally. So there might be a wormhole where you could travel faster than light through the tunnel without violating any fundamental principles. But actually doing so would require technology that we can't even imagine. A wormhole might be traversable, but only for particles, not macroscopic objects. The throat might be too small to admit anything larger than a single atom. It might expand on the other side, but you'd have to pass through a bottleneck so narrow that only elementary particles could fit. This would make the wormhole useless for any practical purpose. You couldn't send a spaceship through. You couldn't send a probe through. You couldn't send much of anything that we'd consider useful. The space of possibilities is large. And within that space, there might be configurations that are almost practical. Configurations that don't require infinite energy, that don't require perfect exotic matter arrangements, that just might be something that a sufficiently advanced civilization could actually construct. But we don't know. We're still exploring the mathematical landscape. And as we explore it, we keep finding that the practical requirements exceed what seems achievable. Understanding that there are multiple types of wormholes is crucial because it means you can't simply say wormholes are impossible or wormholes are possible. The answer depends on which type you're talking about. Non-traversable wormholes, mathematically certain. Traversable wormholes without exotic matter, probably impossible within general relativity. Traversable wormholes within modified gravity theories, maybe possible. Regular wormholes without black holes, mathematically possible but requiring specific matter distributions. The answer to whether wormholes exist depends entirely on what kind of wormhole you're asking about. This brings us directly to one of the most fundamental problems in wormhole physics, the traversability problem. The reason why, even though wormholes are mathematically allowed, they might be physically useless. Even though the equations predict them, the physics might prevent them from being used. Even though they're theoretically possible, they might be practically impossible. This is the core tension that has defined wormhole research for decades, and it's a tension that hasn't been resolved. The fundamental issue is stability. A wormhole throat, by its very nature, wants to collapse. The gravitational forces trying to squeeze the throat closed are enormous. The curvature of spacetime at the throat is extreme, and if nothing opposes these forces, if nothing pushes back against gravity, then the throat will collapse. It will pinch off. The passage will close. And nothing can cross before that happens. This is not just a practical problem. It's not just an engineering challenge. It's a fundamental feature of how space-time responds to gravity. Think about what happens near a black hole. The gravity is so intense that it curves space-time so severely that a point of infinite curvature, a singularity, forms. The curvature is so extreme that the normal rules break down. At the Schwarzschild radius, the curvature reaches extreme values. And the geometry of the space at the throat of a wormhole is similar. The curvature there is extreme. An extreme curvature wants to become more extreme. It wants to collapse further. The only thing that can prevent this collapse is something that pushes back against gravity, something with negative pressure, something with negative energy, something that repels instead of attracts. In standard general relativity, nothing like this exists. We've never detected negative energy density. We don't have a confirmed mechanism to produce it. We can write equations that describe it mathematically. We can work out the consequences. But whether such matter exists in nature remains an open question, and without it, traversable wormholes remain out of reach. The traversability problem also involves something called energy conditions. These are mathematical constraints that place limits on what kinds of energy distributions are physically allowed. In ordinary circumstances, with ordinary matter, these energy conditions are always satisfied. They're descriptions of how normal matter behaves. The weak energy condition says that the energy density must be non-negative. It says that you can't have negative energy. The strong energy condition says that gravity must always be attractive. It says that no matter can repel gravity. The dominant energy condition says that energy density must exceed the magnitude of energy flow. These conditions are statements about reality. They're encapsulations of the way matter actually behaves. at least the way we've observed it behave. But some of these energy conditions must be violated for a traversable wormhole to exist. Specifically, the null energy condition must be violated. This condition says that the energy density must never be negative. It says that you can't have matter with negative mass or negative energy density. And yet, to stabilize a wormhole throat, you need exactly that. You need a violation of this condition. You need exotic matter. Now, there's something interesting here. The Casimir effect in quantum mechanics shows that negative energy can exist, at least in very limited circumstances. Quantum fields can produce negative energy densities in small regions. But we're talking about tiny, tiny effects. And we're talking about effects that are difficult to control and even more difficult to scale up. To stabilize a macroscopic wormhole would require enormous amounts of negative energy, distributed in just the right way. Not just any negative energy, specific, controlled, stable negative energy. This takes us beyond what quantum effects naturally provide. This creates a paradox of sorts. Normal matter, the matter that obeys the energy conditions, cannot stabilize a wormhole. You need abnormal matter, matter that violates the energy conditions. But we've never observed such matter. We have no evidence it exists. We can make it in equations. We can write down its properties. We can calculate what it would do. But finding it, creating it, using it remains beyond our capabilities and possibly beyond what nature permits. So you're left in a strange position. The mathematics says it's possible. The physics says it requires something unobserved. The engineering would be impossibly difficult. The requirements would be extreme. And yet the mathematics is internally consistent. It doesn't lead to contradictions. It describes a universe where wormholes could exist. So the questions become ever more interesting. Is this a limitation of general relativity itself? Does general relativity describe all possible physics? Or is there some deeper theory that would allow wormholes without exotic matter? Is our current understanding incomplete? Yet researchers don't give up. They keep looking for ways around this problem. They ask whether there are modifications to Einstein's equations that might allow wormholes without exotic matter. Recent work in modified gravity theories, frameworks like F of R, T gravity, suggest that within certain mathematical structures, traversable wormholes might be possible using only ordinary matter. If these modified theories turn out to describe reality better than general relativity in certain regimes, then wormholes might become accessible without the exotic matter requirement. It's a long shot. It requires that Einstein was incomplete, but it's not impossible. Science has been surprised before. They ask whether quantum effects might provide a solution. Quantum mechanics introduces strange phenomena at small scales. Quantum tunneling, superposition, entanglement. Perhaps some quantum effect could help stabilize a wormhole. Perhaps quantum fluctuations could provide the negative energy density needed. Perhaps at the Planck scale, where quantum gravity takes over, entirely new phenomena emerge that we haven't yet understood. The exploration of quantum gravity, the attempt to unify quantum mechanics with general relativity, might reveal new mechanisms for wormhole stability. They ask whether there are configurations of normal matter that, while not being exotic matter, might still do the job. What if you arranged ordinary matter in a very specific, very clever way? What if you exploited some previously undiscovered property of matter? What if there's a loophole in the theorem that supposedly requires exotic matter? These are all long shots, but they're worth exploring because the reward would be enormous. They ask whether wormholes might be created by some process we haven't yet thought of. What if the early universe created wormholes and some of them survived until now? What if there are quantum processes at the Planck scale that continuously create microscopic wormholes? What if dark energy, the mysterious force driving cosmic expansion, is somehow related to wormholes? What if wormholes play a role in the structure of the quantum vacuum itself? And sometimes they find hints. Sometimes the mathematics reveals possibilities. The ER equals EPR conjecture suggests that wormholes might be intimately connected to quantum entanglement. Recent work shows that quantum computers can simulate wormhole physics. Modified gravity theories allow traversable wormholes without exotic matter. The hints are there. They're subtle. They're difficult to interpret. But they suggest that the final answer isn't necessarily no. It might be maybe. It might be yes under conditions we haven't yet discovered. But concrete answers remain elusive. The traversability problem is ultimately about energy. It's about the enormous energy cost of stabilizing a wormhole. It's estimated that to create a traversable wormhole with a throat the size of a single proton, you would need as much energy as a star generates in billions of years. Let that sink in for a moment. A single proton is incomprehensibly small. It's the nucleus of a hydrogen atom. It's 1 billion times smaller than the width of a human hair. And to create a wormhole the size of that tiny particle, you need as much energy as the sun generates in billions of years. The sun, which is so massive that billions of tons of hydrogen fuse into helium every second, generating incomprehensible amounts of energy, takes billions of years to produce the energy needed to stabilize a wormhole 1 proton in diameter. This is not a problem that engineering can solve. This is not a problem that technology can overcome. That's not a future problem waiting for better computers or cleverer techniques. That's a fundamental requirement of the physics. You need that much energy. Period. No way around it. And we don't have access to that kind of energy. No civilization has access to that kind of energy. We can barely harness the energy of our own sun. A Type 2 civilization on the Kardashev scale, one that could harness all the energy of a star, still couldn't create more than a single proton-sized wormhole. And it's hard to imagine that any civilization, no matter how advanced, could ever exceed the energy output of the entire star system they inhabit. This leads to a sobering conclusion. Wormholes, if they're to be traversable at all, if they're to be more than mathematical curiosities, probably can't be created. They can't be engineered. They can't be built. Not by any civilization that uses conventional physics and conventional sources of energy. The energy cost is simply too high. The requirements are simply too extreme. This doesn't mean wormholes can't exist. It means they probably can't be made. They might exist naturally. They might have been created naturally in the early universe. They might be relics of cosmic history, but creating new ones, engineering them, using them, seems fundamentally beyond reach. Yet the fact that the mathematics permits it, that the equations describe it, that it's not forbidden by the laws of physics, keeps the door open. It means that if wormholes are ever discovered naturally, if they somehow exist without having to be engineered, then the traversability problem would be solved automatically. They would already be there, already stable, already open. Someone or something else would have handled the energy requirement, the exotic matter requirement. The universe, in its billions of years of history, might have created conditions that we cannot replicate. The early Big Bang, with its incomprehensible energies, might have created wormholes that have persisted to this day. Black hole collisions might generate wormholes. Quantum fluctuations might birth them at the Planck scale. But finding such a wormhole would be like winning an incomprehensible lottery. The odds would be staggering. The conditions required would be so specific, so rare, that in an infinite universe, you might still not find one. And even if you did, you'd have to recognize it. You'd have to distinguish it from other compact objects. You'd have to confirm it's truly a wormhole and not something else. The observational signatures of a wormhole are subtle. They might look very similar to black holes. They might be indistinguishable without the right measurements. This is where wormhole physics stands today. The mathematics is clear. The equations permit wormholes. The geometry is sound. But the physics is harsh. The requirements are extreme. And the evidence is absent. We have mathematical predictions and not much else. Which means that despite decades of research, despite brilliant physicists working on the problem, despite the elegant mathematics, wormholes remain firmly in the realm of theory. They remain possibilities that the universe is mathematically allowed to have. But whether it actually has them, and whether we could ever use them if it did, those remain profoundly open questions. But there is something worth understanding about this paradox. Exotic matter, for all its strangeness, is not forbidden by the laws of physics. It's not impossible in principle. It's just never been observed. And that distinction matters. The absence of evidence is not evidence of absence when it comes to the fundamental laws of nature. Quantum mechanics suggests that exotic matter might exist in limited quantities, created briefly in quantum fluctuations before annihilating back into nothing. The Casimir effect demonstrates that quantum fields can produce negative energy densities in specific geometric configurations. Plate a few millimeters apart in a vacuum, create a region where the energy density is actually negative compared to the surrounding space. This was predicted theoretically and then confirmed experimentally. So negative energy is not completely unknown to physics. It's just incredibly difficult to produce in useful amounts. The challenge is moving from micrograms of negative energy in a laboratory setting to the enormous quantities needed to stabilize a macroscopic wormhole. The jump is not just quantitative. It's qualitative. It's the difference between a curiosity of quantum mechanics and a cosmic engineering feat. Some physicists argue that exotic matter might be found naturally in the universe, perhaps near the cores of certain black holes, perhaps in the structure of dark energy itself, perhaps in regions of space-time so extreme that our current physics breaks down entirely. The universe has billions of years of history and incomprehensible scales of space. If exotic matter exists anywhere in that vast tapestry, conditions might have aligned to create it. But finding it, if it exists, would require either incredible luck or technology that can probe the deepest secrets of the cosmos. Dark energy itself, the mysterious force accelerating cosmic expansion, has properties that resemble exotic matter in some way. Years. It has negative pressure. It behaves like it has negative energy density on cosmic scales. If dark energy is truly exotic matter, then the universe already contains enormous quantities of it. But dark energy is distributed everywhere, filling all of space uniformly. It's not concentrated in the places where you'd need it for a wormhole. Extracting dark energy and concentrating it would present technical problems beyond anything else we've discussed. You would need to manipulate the fabric of spacetime on cosmic scales. You would need to reach into the vacuum of space itself and reshape it. This transcends the idea of engineering. It approaches the concept of recreating the universe itself. The mathematical requirement for exotic matter in wormholes is not arbitrary. It emerges naturally from the stress-energy tensor, the mathematical object that describes how matter and energy curve space-time. Einstein's equations relate the curvature of space-time directly to the distribution of energy and mass. For normal matter, positive energy density curves space-time inward, creating attraction. This is how gravity works. The Earth's mass curves space-time around it, and we experience that curvature as gravitational pull. But a wormhole throat is different. It requires space-time to curve in a way that keeps the passage open, to repel rather than attract. And the only way to achieve that geometrically is with negative energy density. It's not that physicists chose this requirement arbitrarily. The mathematics of general relativity imposes it. The geometry itself demands it. Einstein's equations are not suggestions or approximations. They're statements about how spacetime fundamentally behaves. And they clearly state what's needed to keep a wormhole open. This is what makes exotic matter so central to wormhole physics. It's not an optional accessory. It's a necessary consequence of the geometry. To understand why this is true requires understanding something called the null energy condition. This is one of several energy conditions that describe how matter and energy can behave. The null energy condition states that the energy density must never be negative. It says that the product of energy density and the speed of light squared must always be greater than or equal to 0. This condition is satisfied by all normal matter in the universe. Every particle, every field, every form of energy we've ever observed obeys it. But a traversable wormhole requires this condition to be violated. It requires matter with negative energy density, matter where the energy density is less than 0. This violation seems unnatural. It seems wrong. It seems like it should be forbidden by the laws of physics. And yet, general relativity doesn't forbid it. The equations of general relativity can accommodate negative energy density. They can use it. They can build wormholes with it. The null energy condition is important, but it's not absolutely fundamental. It's a property of the matter we know about, not a requirement of the theory itself. There are theories that might circumvent this requirement. Some physicists have proposed that modified gravity theories, alternatives to general relativity that work better at certain scales, might allow wormholes without exotic matter. In modified gravity, the rules change slightly. The relationship between matter and space-time curvature becomes more complex. And in some versions, traversable wormholes emerge using only ordinary matter. If one of these modified theories turns out to be the correct description of gravity at scales we haven't yet probed, then the exotic matter requirement might vanish. The wormhole could become more accessible. But this requires that Einstein was incomplete, that his equations don't capture the full story of gravity. It requires that nature works differently than we currently understand. It's possible. Science has been wrong before, but it's also speculative. General relativity has been tested to extraordinary precision. It survived every experimental challenge for over a century. Replacing it with something new would require overwhelming evidence. Modified gravity theories exist, but they're not yet preferred by the observational evidence. So for now, exotic matter remains the most likely requirement for traversable wormholes within our current understanding of physics. The amount of exotic matter needed is staggering. To stabilize a wormhole the size of a proton, you'd need negative energy equivalent to the power output of billions of stars over billions of years. To stabilize a wormhole large enough for a spacecraft to pass through, the energy requirement becomes incomprehensible. It would exceed the total energy available in observable universe by many orders of magnitude. These are not engineering problems that can be solved with better technology. These are fundamental limitations imposed by the physics itself. A civilization would need to harness energy sources far beyond anything we can imagine. They would need to manipulate negative energy in ways we haven't conceived of. They would need to do something that essentially requires reshaping the laws of physics themselves. And yet, even with these constraints, physicists continue to work on the problem. They keep asking whether there's a way, whether there's a loophole, whether there's some clever arrangement that makes the requirement less severe. This is the nature of theoretical physics. You follow the mathematics wherever it leads, even when it leads to seemingly impossible conclusions. Because sometimes, the seemingly impossible turns out to be merely very difficult, and sometimes, the very difficult becomes routine through innovation and understanding. The practical implications of the exotic matter requirement are worth pausing on. If a traversable wormhole requires exotic matter, and exotic matter either doesn't exist or exists only in forms we can't access, then wormholes aren't something you can build. They're not something you can engineer into existence through clever design or advanced technology. At best, they're something you might find. Something that nature created under conditions that haven't been repeated since. Finding such a wormhole would be finding evidence of either a natural process we don't understand, or evidence that something else created it. The latter has profound implications. If wormholes are found, physicist Ron Gamble has suggested that they must have been constructed by something. Whether that's a past civilization from our own universe or something from elsewhere, the discovery would rewrite our understanding of what's possible. But finding them would require distinguishing wormholes from black holes and other compact objects, a task that requires observational tools we're only beginning to develop. And even if wormholes exist naturally, they might be in places we can never reach. In regions of space-time cut off by cosmic expansion, in the cores of distant galaxies, in quantum foam at scales too small to access. The universe is vast, and wormholes, if they exist at all, might hide in places we never reach. The requirement for exotic matter has also led some physicists to question whether the universe is constructed in a way that forbids shortcuts. Perhaps there's a fundamental principle we haven't discovered yet, something deeper than general relativity that prevents time-traveling wormholes while allowing static ones. Perhaps nature has built-in safeguards against paradoxes. Perhaps the universe, at its deepest level, prevents configurations that would violate causality. Hawking has speculated about such a chronology protection conjecture, the idea that the laws of physics are set up to prevent time travel even if the mathematics temporarily permits it. If such a principle exists, it might also apply to wormholes used for spatial shortcuts. It might require conditions so impossible to achieve that wormholes remain forever theoretical. This is speculation, but it's the kind of speculation that keeps theoretical physicists occupied. The universe seems designed with remarkable precision. Perhaps that precision extends to forbidding wormholes entirely, or perhaps it merely makes them extraordinarily rare and difficult to access. Building a wormhole, even theoretically, requires working through mathematics that becomes increasingly complex at every step. Start with the Einstein field equations, the fundamental laws governing spacetime. These are 10 coupled, nonlinear partial differential equations. Solving them exactly is extraordinarily difficult. You've succeeded if you can find even one exact solution, and there are only about a dozen known exact solutions for interesting configurations. Any solution you want to use for a wormhole must satisfy the equations everywhere throughout space-time, not just in some local region. It must be consistent everywhere at all times. This is a remarkable constraint. It means that the solution must work from the infinitesimal to the cosmic scales, from quantum fluctuations to the structure of the universe itself. Every part must fit together perfectly. The Schwarzschild solution is one of these exact solutions, and it naturally contains wormholes within its geometry. But as we discussed, those wormholes are non-traversable. The throat pinches off too quickly. To make a wormhole traversable, you must modify the solution. You must add something that keeps the throat open. And whatever you add must still be a solution to Einstein's equations. This is where the mathematics becomes truly constraining. You can't just add anything. Whatever you add must be consistent with the fundamental laws. It must fit into the geometry properly. And when you work through the calculations, requiring that a wormhole throat remain open while still satisfying all the constraints of general relativity, exotic matter is what emerges. It's not a choice. It's an inevitability of the mathematics. Morris and Thorne worked through this in the 1980s and showed that a traversable wormhole could be constructed if you distributed exotic matter in a very specific way. A thin shell of exotic matter with negative energy density lining the throat, repelling gravity and holding the passage open. This is the Morris-Thorne wormhole, and it represents the minimal exotic matter configuration that works. It's elegant in its simplicity. It's also completely fictional in terms of practical construction, because distributing exotic matter in such a precise way would require technology that manipulates the fundamental structure of space-time itself. It would require being able to control quantum fields on macroscopic scales. It would require understanding and harnessing energy in ways we can barely theorize about. To actually build such a wormhole, you would first need to source the exotic matter, or create it, or discover it. None of these are feasible with current technology. Assuming you somehow obtained the necessary exotic matter, you would then need to construct the wormhole mouth. You would need to take a region of space-time and induce it to become a wormhole. You would need to manipulate the metric, the fundamental description of distances and time intervals in space-time, to have the wormhole structure. This is roughly equivalent to reaching into the fabric of reality and reshaping it. Again, not feasible. But even in thought experiment, let's imagine you could do this. You would need to be careful about the total energy involved. The energy cost isn't just in the exotic matter. There's energy in the space-time curvature itself. A wormhole of useful size might contain more energy than your civilization produces in a millennium. This energy isn't something you can just pump in gradually. It's locked into the structure of space-time itself. Once created, it stays there. You can't turn off a wormhole the way you turn off a machine. It would persist until the exotic matter somehow dispersed or the universe itself changed. Creating a wormhole would be an irreversible modification to the cosmic structure. This raises questions about cosmic engineering. If your civilization created a wormhole, you would be permanently altering the geometry of space-time in your region of the universe. Other civilizations, if they exist, might be affected. Light traveling near the wormhole would be deflected by its gravity. Objects in orbit around it could be disrupted. The wormhole becomes a permanent feature of the cosmic landscape. Future civilizations might find it and wonder who built it. Or they might find it catastrophically. A wormhole encountered unexpectedly could be dangerous. A spacecraft might fall into it accidentally. A civilization might not realize what they're dealing with until it's too late. These might seem like far future concerns, but they illustrate how profound an act wormhole creation really is. It's not like building a machine or a structure on a planet. It's modifying the universe itself. The stability of the wormhole you created would be another concern. The Morris-Thorne wormhole is mathematically stable under certain conditions. But stable mathematics doesn't necessarily mean stable physics. Small perturbations, tiny variations from the perfect configuration, might cause instabilities that grow over time. A real wormhole might be fragile, sensitive to disturbances. A particle passing through could disrupt the balance. Quantum fluctuations in the exotic matter could cause it to decay. The wormhole might collapse minutes or days after its creation, or it might be genuinely stable and persist indefinitely. Without being able to actually create one and test it, we simply don't know. The mathematics provides a framework, but nature has the final say. There's also a problem called the cosmic string instability. In some formulations of wormhole physics, a wormhole threaded with an exotic matter distribution can be stabilized by a cosmic string, a theoretical defect in space-time created in the early universe. If cosmic strings exist, and if they could be used to prop open a wormhole throat, this might provide an alternative to the exotic matter requirement. But cosmic strings themselves have never been observed. And even if they exist, the problem of sourcing, positioning, and controlling them to create a wormhole would be just as severe as sourcing exotic matter. It's trading one speculative requirement for another. The fundamental problem remains unsolved. Some physicists have explored whether quantum entanglement itself could serve the role of exotic matter. In the ER equals EPR conjecture, wormholes are connected to quantum entanglement. Perhaps highly entangled quantum states could stabilize a wormhole throat. The entanglement would provide the repulsive effect needed to keep the passage open. This is more promising than purely classical exotic matter because entanglement is something we can create and manipulate in laboratories. We can generate entangled pairs. We can maintain entanglement under certain conditions. But scaling this up from laboratory conditions to macroscopic wormholes presents enormous difficulties. You would need to maintain quantum entanglement across scales of centimeters, meters, kilometers. Entanglement is fragile. It breaks down easily. Environmental disturbances, heat, vibrations, anything can destroy it. Keeping a macroscopic region of space in a highly entangled state, precisely enough to stabilize a wormhole, might be impossible. The thermal noise in any realistic environment would destroy the entanglement faster than it could support the wormhole. Again, we're left with a beautiful theoretical possibility that seems practically impossible to achieve. Even supposing you built a stable wormhole and kept it open, you would face the problem of actually using it. The wormhole throat might be surrounded by extreme conditions, powerful gravitational fields perhaps, intense radiation, space-time curvature so severe that being near it would be lethal. A spacecraft entering the wormhole would need shielding beyond anything we can engineer. The crew would experience tidal forces that might stretch them into atoms. The radiation might cook them instantly. The space-time curvature might be so extreme that the equations of general relativity themselves break down, and you enter a regime where quantum gravity takes over. At that point, you're no longer in the realm of classical physics. You're in territory where our theories are incomplete. But let's imagine you solved all these problems somehow. Let's imagine you created a stable, traversable wormhole and figured out how to pass through it safely. You would then reach the other side. And what would be there? If the wormhole connects to a distant region of the same universe, you would emerge billions of light years away, having traversed the distance through space-time in what might be a short time. If the wormhole connects to a different universe, you would emerge in an entirely different space-time with potentially different physical laws. The discovery would be revolutionary, but the practical utility would depend on where the other end goes. A wormhole that connects to the nearest star might be useful. A wormhole that connects to a random location in a distant galaxy would be less so, and a wormhole whose endpoint you can't control would be useless. The problem of wormhole mouth positioning is another unsolved challenge. If you create a wormhole, where does it connect? How do you control where the other end appears? Current theory provides no way to determine this. It might be fixed by the initial conditions you create the wormhole under. It might be random. It might be determined by quantum uncertainty. But there's no known way to choose the destination. You would create a wormhole at random and hope the other end connects somewhere useful. Given the vastness of space-time, the odds of connecting to something useful would be vanishingly small. Consider the scale of this problem. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star might have planetary systems. The total volume of space-time containing matter and energy spans billions of light years. Now consider creating a wormhole and hoping its other end connects to Earth, or to any particular star system you'd actually want to reach. The probability is incomprehensibly small. It's like firing an arrow blindfolded and hoping to hit a specific grain of sand on a beach that spans the entire planet. And yet, mathematically, there's no constraint in general relativity preventing you from creating such wormholes. Nothing stops you from creating hundreds of them in random directions, hoping some lucky configuration connects somewhere useful. But this isn't a strategy. This is desperation. A working wormhole network would require technology to control where wormhole endpoints connect. Technology that doesn't exist and might not be possible. The inability to control wormhole destination is not just an engineering problem. It's a fundamental gap between what the mathematics permits and what practical use requires. So building a wormhole, even theoretically, reveals layer after layer of practical impossibilities. Each problem has solutions in principle, but each solution creates new problems. Each step forward requires capabilities we don't have and might never have. Yet the mathematics describes it as possible. The equations permit it. The geometry allows it. And that disconnect between mathematical possibility and practical feasibility is what makes wormholes so frustrating and so fascinating to physicists. They exist in the realm of theory with remarkable clarity. But the gulf between theory and practice is vast beyond measure. Consider another layer of the problem. A wormhole that's traversable requires not just exotic matter, but the right amount of exotic matter distributed in the right shape. It needs to be thin, efficient, tightly concentrated. Any waste, any inefficiency, and you need exponentially more exotic matter. If the exotic matter is spread out even slightly, the energy requirements multiply. If it's clumpy rather than smooth, the wormhole becomes unstable. The margin for error is essentially zero. You need perfect precision in a regime where perfection is impossible. Quantum mechanics doesn't allow perfect precision. The uncertainty principle forbids it. You can't know both the position and momentum of a particle with arbitrary precision. So at the quantum level, your exotic matter distribution will have fluctuations. These fluctuations could seed instabilities that grow and destroy the wormhole, or they might be negligible. Without actual experimental data, we simply don't know. The wormhole might be robust to quantum fluctuations, or it might be fragile, collapsing at the slightest disturbance. This uncertainty adds yet another layer to the list of unknowns. And the more unknowns pile up, the less feasible the entire project becomes. Moving into time travel implications brings another layer of complexity entirely. If wormholes could be used to travel not just across space, but through time, the paradoxes become acute. Time travel is mathematically possible in general relativity. Closed time-like curves, paths through space-time that loop back on themselves, can exist under certain conditions. A wormhole that connects 2 points not just at different locations, but at different times could create such curves. It could allow you to travel into the past. And if you can travel into the past, you run into the grandfather paradox immediately. But this paradox isn't actually paradoxical when examined carefully. It's a logical consistency problem, not a physical one. If you travel back in time and prevent your own birth, you reach a contradiction. You can't prevent your birth because then you wouldn't exist to travel back in time. But Stephen Hawking pointed out that consistency can be maintained. The laws of physics simply prevent you from doing anything that would create a logical contradiction. If you try to prevent your own birth, something will stop you. A gun will jam. A hand will slip. The circumstances will conspire to prevent the paradox. The universe, it seems, is self-protecting. It maintains consistency because the laws of physics enforce it. This principle, called the self-consistency principle, or chronology protection conjecture, suggests that even with a time-traveling wormhole, you cannot change the past. You can visit the past. You can interact with it. But anything you do will necessarily be part of the historical record. Whatever you do in the past was already done. You were always there. Your actions were always part of history. You cannot create a paradox, because paradoxes are forbidden by the universe itself. This seems strange at first. It seems to deny free will. If you travel back in time, you cannot make different choices. Whatever you choose to do was already your choice in the historical record. But this resolves the paradoxes. The universe remains consistent. Causality is preserved, albeit in a strange form where the timeline is locked into a single consistent configuration. Think of the universe as a completed tapestry rather than an unfolding story. Every thread is already in place. Every color is already set. If you travel backward through that tapestry, you discover that you were always part of it. Your actions in the past are woven into the pattern. You might think you have free will, that you can make different choices when you arrive in the past. But your free will operates within the constraints of the tapestry. Whatever you choose to do, it's already part of the pattern. This creates a strange kind of determinism, not imposed from outside, but arising from the consistency requirement itself. Some physicists are uncomfortable with this resolution. It seems to deny free will too much. It suggests that the universe is deterministic at the deepest level, that every event is predetermined and unchangeable. Others argue that quantum mechanics introduces randomness, that free will is compatible with determinism in certain frameworks. The debate continues, but the mathematics is clear. The self-consistency principle works. It prevents paradoxes. Whether it's the final word on time, travel remains open. Hawking himself was somewhat uncomfortable with the principle. He preferred the idea of chronology protection, that the universe is set up in such a way that wormholes that create closed time-like curves simply cannot form. He suggested that some deeper principle, some law of physics we haven't discovered yet, forbids them. If Hawking was right, then wormholes might exist, but only the space-like variety. Only wormholes that connect different locations, not different times. This would avoid the paradoxes entirely, but it would also eliminate one of the most interesting possibilities that wormholes suggest. There's another possibility worth considering. What if wormholes could connect different universes? What if they could allow travel not just backward in time, but to alternate timelines or parallel realities? This opens up entirely new possibilities and problems. In a multiverse framework, where many universes exist, with slightly different physical laws or different histories, wormholes could be bridges between them. The grandfather paradox would vanish. You could change the past in an alternate universe without creating any logical contradiction. You would simply be affecting a different timeline than the one you came from. This is more appealing philosophically. It preserves a sense of agency and causality. You can make different choices. Those choices have consequences. But they happen in a different universe, so they don't create paradoxes in your universe of origin. Whether such multiversal wormholes are possible is unclear. They would require exotic matter, just like single universe wormholes. They would face all the same construction and stability problems. But mathematically, general relativity permits spacetime configurations that connect different universes. The theory doesn't forbid it. Whether nature actually allows it is another question entirely. The implications of time travel through wormholes extend far beyond the technical feasibility. They raise profound philosophical questions. If you can change events in the past, do you have free will? If the universe prevents paradoxes through self-consistency, is anything truly undetermined? If wormholes connect to other universes, are you responsible for consequences in those universes? These questions don't have easy answers. They challenge our intuitions about causality and responsibility. A civilization with access to time-traveling wormholes would face moral and practical dilemmas we can barely conceive of. They would need to grapple with the responsibility of their actions backward through time. They would need to understand how their choices propagate through the timeline. They would need frameworks of ethics and law that extend across time in ways our current systems don't. And if mistakes are made, if someone creates a paradox or disrupts another timeline accidentally, the consequences could be severe. In some thought experiments, a disrupted timeline could retroactively erase universes. It could cascade through history and destroy past and future simultaneously. These scenarios are speculative, but they highlight how dangerous time travel really is. It's not just a practical problem, it's a conceptual problem. It's a challenge to our understanding of reality itself. A civilization with access to time-traveling wormholes would need to develop frameworks of ethics and responsibility that extend through time in ways our current legal and moral systems cannot accommodate. They would need to understand backward causation. They would need to grapple with the fact that their actions ripple through history in both directions. They would need to make decisions knowing that those decisions propagate into the past. This could lead to paralysis. How do you act knowing that your actions might undo your own history? How do you make a choice knowing it might erase yourself or others retroactively? These are not academic questions if time travel becomes possible. They're existential problems. For these reasons, many physicists believe that time travel through wormholes, even if mathematically possible, might be prevented by some deeper principle we haven't discovered yet. The universe might enforce a chronology protection principle at a level we don't yet understand. It might prevent wormholes that create closed time-like curves. It might allow only space-like wormholes that preserve the timeline. Or it might forbid wormholes entirely. We don't know. But the fact that time travel leads to paradoxes, even if those paradoxes can be resolved mathematically, suggests that nature might have built-in safeguards against it. Perhaps the universe is fundamentally forward-moving. Perhaps causality isn't just a feature of how we observe reality, but a deep requirement of how reality operates. Perhaps time is genuinely directional in a way that no mathematics can overcome. If so, then time travel remains firmly in the realm of impossibility, even with exotic matter and traversable wormholes. The mathematics might describe it. The equations might permit it. But the underlying structure of reality might forbid it absolutely. 1. Observational possibilities. How we might detect wormholes through gravitational lensing, gravitational waves, and accretion disk analysis, with comparison to how black holes transitioned from theory to observation. 2. Quantum wormholes. The ER equals EPR conjecture, quantum entanglement stabilization challenges, and the quantum simulation experiments. 3. Alternative theories. Modified gravity theories that might permit wormholes without exotic matter. 4. The mystery remains. Philosophical exploration of the unknowns and the significance of wormholes to physics. But finding a wormhole, if they exist, would require observational tools far beyond anything we currently possess. The problem is fundamental. A wormhole mouth would look remarkably similar to a black hole from a distance. The gravitational lensing, the way light bends around the object, the distortion of space-time in the surrounding region, all of these would appear nearly identical for a non-rotating black hole and a Morris-Thorne wormhole. Both objects curve space-time dramatically. Both pull light around them through gravitational influence. Both create that characteristic shimmer and distortion we associate with extreme gravity. The difference is in what happens when light or matter gets very close. For a black hole, there's a point of no return. Cross the event horizon and you're gone forever. Light cannot escape. Information cannot escape. It's a one-way door into oblivion. For a wormhole, in theory, you could pass through. You could emerge on the other side. But from a distance, before you reach that critical threshold, the signatures are nearly identical. This is why detecting wormholes requires gravitational lensing analysis with unprecedented precision. astronomers study how light from distant objects bends as it passes near massive structures. The patterns of bending, the subtle variations in how the light distorts, could reveal differences between black holes and wormholes. But those differences are incredibly subtle. They require measurement tools that barely exist and might not exist for decades. Current telescopes can image black holes now. The Event Horizon Telescope captured the first images of black hole shadows in recent years. These images showed the characteristic dark region at the center, surrounded by glowing matter and magnetic fields. But detecting the difference between a black hole and a wormhole would require even more precision. The shadows might look different. The shape of the accretion disk, the way matter orbits the object, the pattern of radiation emission, all of these could potentially reveal which type of object you're observing. But subtle is an understatement. We're talking about detecting variations in angles of a few arc seconds across distances of millions of light years. We're talking about distinguishing between objects whose main visual characteristics are nearly indistinguishable, except under extreme conditions of observation and analysis. To get a sense of the difficulty, consider the challenge of measuring the angle between two stars as seen from Earth. The resolution limit of even our best telescopes is measured in fractions of arc seconds, tiny angles that correspond to the apparent separation of objects at enormous distances. Now imagine that instead of measuring the separation between stars, you're trying to measure subtle variations in how light bends around an object millions of light years away. You're looking for deviations from expected patterns, for anomalies that might suggest an unusual gravitational field. You're searching for a signature that might be only slightly different from the standard black hole signature. The precision required pushes the boundaries of what's technically possible. The Morris-Thorne wormhole creates a specific type of gravitational lensing signature that differs from a Schwarzschild black hole in measurable ways. The deflection angle of light rays depends on parameters like the wormhole's throat radius and the distribution of exotic matter. This could be detected if we had the right instruments and the right conditions. A wormhole near a bright source of light or radiation, for instance, would be easier to detect than one in empty space. A wormhole acting as a lens for light from a distant galaxy or quasar could reveal its nature through the precise pattern of lensed images. Multiple images of the same distant object appear when a massive structure acts as a gravitational lens. The positions and intensities of these images carry information about the lensing object. A trained analysis could reveal whether the lensing source is a black hole or a wormhole. But this requires luck as much as technology. The wormhole would need to be positioned just right. The light source would need to be behind it from our perspective. The alignment would need to be nearly perfect. And we would need instruments sensitive enough to detect the subtle differences. This is why many physicists consider wormhole detection a problem for the far future. Perhaps in 100 years, perhaps in 1,000, astronomy will advance enough to make such observations routine. For now, it remains theoretical. We can calculate what the signatures should look like. We can build mathematical models of what astronomers should search for, but we cannot actually see wormholes. Not yet. And we might never find them. Absence of detection doesn't prove absence of existence, but it does suggest that either wormholes don't exist, or they're far rarer than theoretical possibilities suggest. There's another detection method being pursued by some physicists. Gravitational waves. When massive objects collide or move through space, they create ripples in the fabric of spacetime itself. These waves were first detected in 2015, when two black holes merged, and the collision sent ripples that spread through the entire universe. Sensitive detectors on Earth picked up those waves. The detection opened an entirely new way to observe the cosmos. Now physicists wonder whether wormholes would produce gravitational wave signatures. If a wormhole existed near a black hole or neutron star, the interactions between them might create distinctive wave patterns. The collision of two wormholes, if such an event could happen, would produce waves different from any black hole merger. The signature W would be unique. The problem is that gravitational wave detection requires events. You need something to happen. The universe constantly produces black hole mergers and neutron star collisions. These events occur millions of times per year across the cosmos. Wormhole events, by contrast, would be extraordinarily rare if wormholes even exist at all. We might need to listen for gravitational waves for centuries before detecting a wormhole-related event. It's possible. It's in the realm of what's conceivable. But it's also entirely speculative. The next generation of gravitational wave detectors, planned for the coming decades, will be far more sensitive than current instruments. They might be able to detect waves from wormhole events that current detectors would miss. But whether they'll actually find such events is unknowable. We're searching for something we're not even sure exists, looking for signals we're not entirely certain would be produced, using instruments that are still being designed and built. It's the essence of frontier physics. You ask a question, you build tools to answer it, and sometimes the tools reveal nothing, not because the question is unanswerable, but because the answer is no. The frustration lies in the fact that wormholes, if they exist, might be hiding in plain sight. They could be masquerading as ordinary black holes in distant galaxies. They could be orbiting stars undetected because no one has looked closely enough or with the right instruments. The cosmos is vast beyond comprehension. There are billions of galaxies, each containing billions of stars. If even a tiny fraction of a percent of these objects are wormholes rather than black holes, there would still be millions of wormholes out there waiting to be distinguished from their more familiar cousins. Finding them would require systematic observation, careful analysis, and perhaps more than a little luck. The real question might not be whether wormholes exist, but whether humanity will ever develop the means to confirm their existence. We are limited by our technology. We are limited by our position in space and time. We are limited by the speed of light itself, which prevents us from reaching distant regions to examine them up close. These limitations are not permanent. Science advances. Technology improves. Future generations might look back at our current observation tools and wonder how we managed to do astronomy with such primitive equipment. But that advancement takes time, resources, and sustained effort. And there's no guarantee that when wormholes are searched for in such detail, they'll actually be found. There's also the possibility that wormholes might be detected indirectly through their effects on nearby matter and radiation. A wormhole would create a unique gravitational field. Objects orbiting it would move in specific patterns. The orbital mechanics would be distinctive. Radiation falling into a wormhole might produce different X-ray patterns than radiation falling into a black hole. The accretion disk around a wormhole would have different properties because matter wouldn't disappear beyond an event horizon. It would continue to exist and interact with the wormhole's gravity field indefinitely. This could create observable differences in how the accretion disk radiates and evolves over time. An accretion disk is essentially matter spiraling inward. As it falls, friction heats it up. The friction between particles creates radiation, heat, light, and sometimes incredibly violent outbursts of energy. For a black hole, matter spirals down and eventually crosses the event horizon. After that, we can't see it anymore. It's gone from our universe, at least in any conventional sense. But for a wormhole, matter might accumulate differently. It might create patterns of radiation that persist longer. It might show behaviors that contradict what we'd expect from a black hole. A wormhole accretion disk might be hotter, colder, or more active than its black hole counterpart. It might show fluctuations in brightness that reveal the different underlying physics. These are subtle signatures, but they're not impossible to detect if you're looking for them with the right instruments and the right knowledge of what to expect. But again, these differences would be subtle, and detecting them would require comparing observations of multiple objects and looking for patterns that distinguish wormholes from black holes. The challenge isn't just technological, it's also statistical. Even with perfect instruments, you need enough observations to be sure you're seeing a real pattern rather than statistical noise. You need multiple candidate objects. You need observations of their properties over extended periods. You need to rule out alternative explanations. This is why many physicists think wormhole detection, if it happens at all, will be a process that unfolds over decades or centuries. Gradually, as telescopes improve and observations accumulate, patterns might emerge. Anomalies in the properties of certain objects might build a case that some of them are wormholes rather than black holes. But proof would require extraordinary evidence. The case would need to be overwhelming. Because right now, the null hypothesis is that wormholes don't exist. They're mathematical possibilities, not observed phenomena. Until someone shows otherwise, skepticism is the only rational response. The universe has no obligation to contain every object that mathematics permits. Just because Einstein's equations allow wormholes doesn't mean the cosmos bothers to create them. Nature is under no requirement to be generous with its exotic objects. Yet there's something worth noting about how we've approached the search for other exotic objects. For decades, black holes were considered purely theoretical. The mathematics described them clearly. The theory predicted they should exist. But physicists doubted that nature actually made them. Black holes seemed too extreme, too unlikely, too destructive. They were fascinating thought experiments, nothing more. Then observational astronomy advanced. Telescopes became more sensitive. Astronomers found objects moving in patterns that only made sense if they were orbiting black holes. Stars spiraling into black holes. Accretion disks surrounding them, radiation patterns matching theoretical predictions. Eventually, the evidence became overwhelming. Black holes had to exist. They were real. The theoretical became practical. The imaginary became visible. This historical pattern is worth considering when we think about wormholes. We went from thinking black holes were impossible to finding them everywhere. We went from treating them as mathematical curiosities to building observatories designed to study them specifically. This transformation took decades, but it happened. It's not unreasonable to wonder if wormholes might follow a similar arc. Today, they're purely theoretical, dismissed by many as too exotic, too impractical, impossible to build or detect. But the history of black holes teaches us that today's impossibilities can become tomorrow's observations. If astronomy continues advancing, if our tools keep improving, if our theoretical understanding deepens, maybe in some distant century, someone will point a telescope at a distant star system and say, "That's not a black hole, that's something else. That's a wormhole. We finally found one." And the history books will mark the moment when theory became observation, when imagination became reality. The detection might come as a surprise. It might come through an unexpected avenue that no one currently predicts. Or it might come through exactly the channels we're developing now, through gravitational lensing studies or accretion disk analysis or gravitational wave observations. We can't know. But the possibility is there. The mathematical framework is in place. The tools are being developed. The search has begun, even if subtly. Until then, wormholes remain mysteries wrapped in mathematics, waiting to be either discovered or dismissed by the universe itself. They stand at the threshold between what is theoretically possible and what is physically real, and we're still working out which side of that threshold they ultimately occupy. Quantum mechanics offers another avenue for understanding wormholes, one that might not require exotic matter or impossible engineering. The connection between quantum entanglement and wormholes, suggested by the ER equals EPR conjecture, opens possibilities that weren't obvious when physicists focused purely on general relativity. In 2017, physicists showed theoretically that quantum entanglement could stabilize a wormhole. The idea is strange but elegant. When two particles are entangled, they share a quantum state across any distance. Measuring one instantly affects the other, no matter how far apart they are. This seems like it violates everything we know about locality and causality. Einstein called it spooky action at a distance and was deeply uncomfortable with it. But quantum mechanics is clear. Entanglement is real. It's been confirmed experimentally thousands of times. And if quantum entanglement can exist, perhaps it can be leveraged to solve the wormhole problem. Imagine taking an enormous number of entangled particles and arranging them to line the throat of a wormhole. The quantum state they share might create an effect similar to exotic matter. Instead of a repulsive gravitational field, you'd have a quantum effect that prevents the wormhole from collapsing. The entanglement would hold it open from the inside, so to speak. This is radically different from requiring actual exotic matter. Entanglement is something physicists can create in laboratories. They can generate entangled pairs of photons. They can maintain entanglement in certain quantum systems. If the mathematics works out, and if the effect scales up to macroscopic sizes, then suddenly wormhole stabilization moves from impossible to merely extraordinarily difficult. This is why the ER equals EPR conjecture excited so many physicists. It suggested a bridge between quantum mechanics and general relativity, two theories that normally don't talk to each other. General relativity describes the very large, gravity, space-time, the cosmos. Quantum mechanics describes the very small, particles, probability, uncertainty. They're incompatible in most ways. They give different answers to fundamental questions. They use different mathematical frameworks. But wormholes might be a place where they intersect, a place where quantum and gravitational effects become equally important. If wormholes can be stabilized by quantum entanglement, then understanding them requires understanding both theories simultaneously. This is also why wormholes are so valuable to theoretical physicists. They're not just potential transportation devices. They're a way to explore the relationship between the quantum and gravitational realms. Solving the wormhole problem might unlock the door to quantum gravity, the unified theory that physicists have been chasing for nearly a century. The practical problem with quantum entanglement stabilization is scaling. Creating entangled pairs of photons in a laboratory is straightforward. Maintaining entanglement in a few particles is manageable. But scaling this up to trillions or quadrillions of entangled particles, maintaining that entanglement at high temperatures, doing it reliably and predictably, these are challenges that might never be overcome. Entanglement is fragile. It breaks down with any disturbance. Heat destroys it. Vibrations destroy it. Electromagnetic radiation destroys it. Even the act of observing the entanglement too closely can destroy it. In physics, this is called decoherence, the process by which a quantum system loses its quantum properties and becomes classical. It's the enemy of quantum computing, quantum communication, and apparently, quantum-stabilized wormholes. Keeping an entire structure the size of a wormhole mouth in a state of quantum entanglement would require isolating it from every possible disturbance. It would need to be colder than the depths of space, free from all radiation, utterly isolated from external interference. In other words, it would need to be in the most protected environment imaginable, and even then, maintaining the entanglement would require active stabilization. The moment you stopped putting energy into maintaining it, the entanglement would decay. A wormhole stabilized by quantum entanglement wouldn't be a passive structure. It would require continuous power input. It would be like trying to hold open a door against a hurricane. The moment you stopped pushing, the door would slam shut. This creates a technological barrier perhaps even higher than the exotic matter requirement. Because, at least with exotic matter, you could imagine creating it once, and then it stays there. The wormhole remains open indefinitely. With entanglement, you're committed to maintaining an active system forever. One power failure and the wormhole collapses. One glitch in the stabilization system and it's gone. A microsecond of interrupted power and your carefully constructed wormhole vanishes. This is why some physicists prefer the exotic matter model, even though exotic matter doesn't exist. At least in principle, exotic matter would be stable. A wormhole held open by exotic matter would last as long as the exotic matter persisted. There would be no maintenance required. With entanglement stabilization, you're building something more akin to a perpetual motion machine. You need constant energy input to maintain the quantum state. This energy input has to be absolutely reliable, perfectly consistent, never interrupted. It's not impossible in principle, but it's far more demanding than just creating exotic matter and leaving it alone. It transforms a wormhole from a static structure into a process, something that has to be continuously maintained or it collapses. The engineering challenges become staggering when you think about it in these terms. Yet the ER equals EPR conjecture is still worth pursuing because it suggests a mechanism that might actually work. Exotic matter is theoretical and unobserved. Entanglement is real and observable. If physicists can figure out how to leverage entanglement to stabilize wormholes, they might have a path forward. The research is ongoing. Theoretical calculations continue. Computer simulations explore the mathematics. And occasionally, there are experimental results that seem promising. Researchers at Caltech and Google simulated a wormhole-like structure in a quantum computer. They encoded the physics of a traversable wormhole into qubits, the quantum bits that perform calculations. They observed information transfer between entangled systems that mimicked how particles would move through a wormhole. This was not a real wormhole. It was a simulation. But it demonstrated that the underlying mathematics could work. It showed that the connection between entanglement and space-time geometry might be more than just a theoretical curiosity. The beauty of this approach is its elegance. Rather than trying to detect wormholes in the cosmos or build them in laboratories, physicists encoded the entire phenomenon into a quantum system that could be studied and manipulated. It's like creating a miniature version of spacetime and wormhole physics inside a computer. The simulated wormhole behaved according to predictions. Information moved through it as theory suggested it should. The experiment didn't prove that real wormholes can work this way, but it provided evidence that the theory connecting entanglement and spacetime geometry has merit. If quantum computers become more powerful, more stable, and more versatile in coming decades, they might become tools for exploring wormhole physics in depth. They could run simulations of wormhole behavior under conditions impossible to study theoretically. They could reveal whether quantum entanglement can actually serve as a stabilizing mechanism at scales large enough to matter. They could map out the territory of wormhole space in ways we can only dimly imagine now. The simulation also highlighted something profound. If wormholes can be understood as geometric expressions of quantum entanglement, then in some sense, wormholes and entanglement might be the same phenomenon viewed from different angles. A wormhole might be entanglement made visible as space-time geometry. Entanglement might be a wormhole hidden at quantum scales. This would be a remarkable unification. It would suggest that the deepest structure of reality is fundamentally entangled at all scales. Everything is connected. Everything is linked. Every particle in the universe is entangled with every other particle in subtle, imperceptible ways. And on the largest scales, this entanglement patterns itself into the structure of spacetime, creating wormholes, black holes, galaxies, the entire cosmic architecture. The connections between distant objects that seem separate, the hidden links binding reality together, might all be expressions of the same fundamental quantum phenomenon. This is speculative, but it's speculative in the direction that makes physicists excited. It points toward a unified understanding of reality. It suggests that quantum mechanics and gravity aren't incompatible, but are different expressions of the same underlying truth, revealed in different domains, working through different mechanisms, but ultimately speaking the same language. Modified gravity theories offer yet another approach to wormholes that might bypass the exotic matter requirement entirely. Einstein's general relativity is a beautiful and successful theory. It's been tested to extraordinary precision, but it's not the only theory of gravity. Over the past several decades, physicists have developed alternative theories that modify general relativity in subtle ways. These modifications might become important at scales where general relativity breaks down, at extremely high densities, or at the edges of the observable universe. One such framework is called F of R, T gravity, where the gravitational equations are modified to depend not just on the curvature of spacetime, but also on the total matter and energy distribution. In standard general relativity, the gravitational field depends on how matter curves spacetime. In FRT gravity, the relationship is more complex. And it turns out that in some versions of FRT gravity, traversable wormholes can exist without requiring exotic matter. The ordinary matter, the kind that actually exists in the universe, can provide enough gravitational effects to keep a wormhole open. This is revolutionary if true. It would mean that wormholes are not confined to some impossible realm of exotic physics. They could potentially be constructed using normal matter. The challenge is that F of R, T gravity and related modified theories are still speculative. They're not preferred by current observational evidence. General relativity works so well that proving Einstein was incomplete would require extraordinary evidence. Some experiment or observation would need to show behavior that general relativity cannot explain. That hasn't happened yet. So modified gravity remains in the realm of theoretical possibility rather than established science. But the fact that modified gravity permits wormholes without exotic matter is intriguing. It suggests that even if general relativity is the correct description of gravity at the scales we can observe, something more fundamental might underlie it, something that allows wormholes in ways Einstein's theory doesn't. If that's true, then discovering it would rewrite our understanding of gravity itself. It would put us decades or centuries ahead in our ability to understand spacetime. It might finally provide the quantum theory of gravity that physicists have been seeking. These modified theories also suggest mechanisms for how wormholes might form naturally. Perhaps in the early universe, conditions were right for stable wormholes to nucleate and persist. Perhaps some wormholes formed around the Big Bang and have been sitting quietly in remote regions of space ever since. Perhaps there are wormhole populations distributed throughout the cosmos, waiting to be discovered. Perhaps wormholes played a role in shaping the structure of space-time itself as the universe evolved from the Big Bang to its current form. This speculation is built on solid theoretical ground. The mathematics works, the physics is consistent, but without observational evidence, it remains in the speculative realm. The universe has no obligation to follow the paths that physics textbooks suggest. It might have other ideas, other configurations, other solutions to its own equations that physicists haven't considered yet. There's something humbling about that. Here we are, armed with the most sophisticated mathematical frameworks we've ever created, confident in our understanding of how reality works, and yet nature continues to surprise us. Observations reveal phenomena we didn't predict. Theory predicts possibilities that seem to border on the impossible. We build better telescopes and discover unexpected objects. We develop better mathematics and uncover new theoretical possibilities. And somewhere in the gap between what we know and what we don't know, wormholes might exist, waiting quietly for the moment we become clever enough to recognize them. They might be hiding in observations we've already made, visible only to someone who knows how to interpret the data correctly. Or they might be so rare and so distant that finding them requires technology that won't exist for centuries. Or they might be impossible, ruled out by some principle we haven't yet discovered. We simply cannot know until we look more carefully. The mystery of wormholes, then, is not a failure of physics. It's a feature of how science works. We ask questions, we explore the mathematics, we develop theories, and sometimes the theories reveal possibilities that seem to transcend everything we thought was possible. Sometimes they reveal cracks in our understanding. Sometimes they point towards something deeper that we haven't grasped yet. The wormhole is such a possibility. It emerges from our most successful theory of gravity, from the very equations that describe how space-time curves and time flows. The fact that wormholes are permitted by general relativity is not a bug in the theory. It's a feature worth taking seriously. But the fact that wormholes seem impossible to create or detect is also worth taking seriously. Maybe that tells us something. Maybe the universe has built-in safeguards against wormholes. Maybe they're mathematically consistent but physically impossible, the way perpetual motion machines seem possible until you consider thermodynamics carefully. Maybe there's a principle we haven't discovered yet that forbids them, some hidden constraint on how reality can actually construct itself. Or maybe we just haven't been clever enough yet. Maybe future physicists will look back at our current understanding and smile at how limited our imagination was, how we couldn't conceive of the mechanisms that would make wormholes routine. Maybe wormholes are everywhere, obvious once you know how to look, hiding in observations we've already made but haven't yet interpreted correctly. Maybe they're the key to understanding dark matter, dark energy, the Big Bang, and all the mysteries that perplex physics today. Maybe they explain why the universe appears the way it does, and why the laws of physics have the particular values they possess. We simply don't know. The absence of certainty is what makes wormholes so fascinating. They're windows into what physics still doesn't understand. They're mirrors of human curiosity, reflecting back all the questions we haven't yet found answers to. They represent the frontier of theoretical knowledge, the place where our best mathematics reaches its limits, and we're forced to admit that the universe might operate in ways we haven't yet conceived, and perhaps that's enough for now. Not every mystery needs to be solved immediately. Some mysteries are worth thinking about, worth pursuing, worth pondering across generations. Some mysteries demand to be engaged with, even when immediate solutions seem impossible. Wormholes might be such a mystery, remaining eternally at the edge of what science can determine, forever challenging us to think deeper, reach further, and expand what we believe is possible. The holes in space-time might forever remain holes in our knowledge, and that too is an honest truth worth respecting. In the end, wormholes represent something crucial about the scientific process itself. They show us that nature is far stranger than our everyday intuitions suggest. They demonstrate that the laws of physics contain possibilities we might never have imagined without careful mathematical work. They remind us that the universe does not have to be limited by what we think is practical or likely. It can be richer, more complex, more mysterious than we assume. Whether wormholes actually exist in the cosmos or remain purely theoretical constructs, they've already accomplished something significant. They've expanded our sense of what's conceivable. They've shown us that reality might have depths we haven't yet sounded. They've pointed the way toward new frameworks for understanding gravity and quantum mechanics. And perhaps that's the deepest truth about wormholes. They exist in our minds, in our mathematics, in the realm of possibility. Whether they also exist in the physical universe is a question that only future generations, with better instruments and better understanding, will be able to definitively answer. Until then, wormholes remain what they've always been: gateways to the unknown, mysteries that pull us forward, impossible dreams that somehow, mathematically, might be real.